All right, folks. In this video, we'll be giving meaning to a list of edits. This is really like the heart of it, right? Now we're really going to understand, I think, how edits work, and we'll be able to start really talking about algorithms for finding edits from one strand to another, right? You can't do that until you really know how to interpret a list of edits. So, how does it work? Here's the function, apply edits. It takes a strand where we're going to start, right? There's the original strand, and then it takes a list of edits, which we're calling edits, and then it returns the output strand. Now, if you look at this, you look at the match, you can see, oh, this is being defined recursively on its second argument, on the edits, not on the strand. And we'll see why that's important in a minute. Okay, how's it going to work? Well, when we run out of edits, we're just going to return what's left of the strand. Right, there are good reasons for this that I'll talk about in a bit, but let's just say this is what we're going to do. That's just how we're going to do it. Okay, when we have an edit, we've got one. What do? Well, call ApplyEdit, the function from the last video that we spent quite a bit of time talking about, and find out, is there a new base to put on, and what's left of our original strand? Right, so we're going to match on the two things. So this will have type option base, and this will have type strand. Okay, let's ask, is there a new edit to look at? If not, then great. Let's just keep doing recursion, just like keep going with what's left of our original strand and edits prime. Okay, maybe there is some base, right? There's some b that we could do. Okay, well, in that case, let's cons that base that got generated onto our output string and then keep going also. Right? So here you've kind of got some of this sort of filter logic, right? Where we're sort of looking at new to decide what to do. This isn't exactly a map or a filter, though. This is a relatively complicated function that's really sort of like looking at a lot of different stuff to make its decisions, right? Apply edit makes some fairly complicated decisions, and then we use those decisions to make our own decisions. So we're writing some like moderately complex functions at this point, which is pretty cool, right? I think it's also particularly cool how concise this has been. I think a good exercise at this point would be for you to think in whatever language you already know, what would this code look like? How would you talk about edits? How would you define the different notions of edits? How would you write these functions and how would that look? Worth thinking about. Okay, so that's how apply edits works. Um, what we can do from there is start to talk about edits that get us from one strand to another. So we'll say edits are valid if they take us from one source strand to a target strand, right? So to go from source to target with a list of edits is valid if when we apply the edits to the source strand, it's equal to the target. Okay, great. So let's look. So here we've got a bunch of different edits, which should all get us from source to target one. So here's one edit, substitute T for G, and then copy the CAT. Here's another one, delete the G, add a T, and then copy 3. And then here's another one that works, but maybe surprises you. Just substitute the T. That's all my edits. Interesting. Okay, so let's confirm that each of these works. Compute, apply edits, DNA source, edit, target 1. Wow, we got TCAT out. Look at that. It worked. What about edit target 1 worse? Okay, good. What about edit target 1 same? Okay, so we can quickly test this to be like, oh, good. It thinks that they're valid. Now, why do I call these worse and same? Well, what are the costs of these? Well, the total cost of edit target 1, if you look at it, is 1. There's just the one non-copy edit, substitute T. What about edit target 1 worse? Oh, it's 2 because we delete and then we add. Interesting. What about come 2? Also 1. Well, that makes sense, right? Because it's just 1 in it. You might be surprised, though. Why does this work? Funny. Well, let's go back to the function and see why that works. So what's going to happen? We'll do substitute T. Substitute T will return some T and then cat, right, from apply edit. And then we'll do the recursive call with an empty list of edits with t const on. And then, oh, we'll be out of edits. It'll be the empty list of edits because there's just the one substitute in there. And then we return the original strand. A way to think about this is we've said just by default, hey, if I have strand left in my original strand and I run out of edits, just pretend I wrote copy. Just copy the rest of it. Just leave it all alone. So that's fine, right? That doesn't alter the cost of anything. That's part of why we've made sure that the cost of copy is 0, because this has the same cost as this. You can have any number of copies at the end and have it be fine. It doesn't matter. We're only interested in counting the cost of like real edit operations. So this is just as good as this one. Now, the edit algorithms we're going to write are always going to generate a list of edits as long as the input strand, at a minimum. Really, at the maximum length of the two is how many edits it'll generate. So we're never going to have to particularly worry about this case. I wanted to highlight it just as a sort of a sense of like, we're starting to have to deal with these sort of like edge cases where there's no great decision to make for anything. And I've made this one because it sort of like dovetails apply edits with cost, right? If we had changed this instead to just be empty list, well, now we would have these implicit delete edits that would sort of be free, right? Because then we would have substitute t, delete, 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 delete would be the same as this one, but the cost of this would be 4 and the cost of this would be 1. So we really want the default behavior to be the cost-free thing. If that didn't make sense, that's fine. If it did make sense, great. The goal is just to give you some intuition about how I'm making these sort of arbitrary choices in a way that keeps things fitting together. All right, so what you have after this is there's a little exercise where we'd like you to, on your own, come up with edits that get you first from DNA source to DNA target 2, and then from DNA source to DNA target 3. And we've put these little computes here for you so you can check. These should return true when you've got it right. Now, we do have one caveat. Your edit should be minimal, the lowest cost possible, while still being valid. So, okay, you're going to have to think about it a little bit. I think this is a great exercise to do before we do the rest of it because it's going to help build your understanding. But the nice thing is by the end of this day, we'll have an algorithm for computing the optimal edits. So like you could just use that algorithm when you're done. I think it's really best for you to try to figure it out now because it's going to make writing that algorithm make sense, right? Because you're actually the one who has to write the algorithm. I'm just going to explain it. Okay, cool. That's, I think, all I wanted to talk about here. After this, we'll start writing some algorithms for actually producing edits given a pair of strands. All right, see you on the other side.